Hi, welcome to R2E, and this is our second video on quantum mechanics 2. And in this video, we will be doing formal development of perturbation theory. So now we'll be doing it formal development of perturbation expansion. Great. So let's start. Suppose we have an unperturbed Hamiltonian given as H0 and its eigenstates are N0, eigenenergies are En0, something like this, right? Now we have a unperturbed Hamiltonian, and obviously there's the assumption is that they form a complete set. So this implies that if you take a sum over all n, if you take a sum over all n, then this actually goes to identity, right? And now suppose you have a perturbed Hamiltonian where you have h0 plus lambda v, and then you have not the eigenstate, but then you have some new eigenstates given as n, and their energies are n and get n. Okay, now obviously, so the assumption here is that one can use n0 and en0 to get en lambda and n lambda up to different orders, and one can find corrections, as we call them, perturbative corrections. Okay, so before doing that, let's define some things here, right? So so I have h0 plus lambda v, and I'm just going to write this as n, not lambda n, is en minus of en0 plus en0, and again there is, now we define this quantity right out here as delta n. I hope it's fine. So then this is h0 plus lambda v is delta n, which is great, and plus en0. Now I take en to that side and bring lambda n this side. So this will result in h0 minus of en0, and that will be delta n minus of lambda v. Right. Just to make the signs here, I can put it plus here, negative here, and I can put a plus here, negative here, and then this cancels out. And this implies that n0 minus of h0 times get n equal to lambda v minus of delta n get n. Great, so we have our equation. So this will be the equation that we will be solving, the Schrodinger equation that we will be solving and trying to get the perturbed solution n. Okay, great. Now the question here is, so obviously, so one of the ideas is that you would like to just take this quantity here and just take an inverse of here, but note that h0 it acts on n0 to give n0 times get n0, right? So in principle, it doesn't act on n. So how do you manage that? So thankfully, if you take an expectation value with respect to n, so you have en0, and once this n0 will hit h0, it will also give you n0 and obviously n, and here you will have n0 lambda v minus of delta n get n, so which is equal to 0. So you're safe in that sense that your lambda v minus of delta n get n is actually orthogonal. So let me just put a perpendicular sign, which is not correct in all principle, but let's just say it denotes that it's orthogonal. So it's orthogonal to the n0, like the unrest state, right? And great. So now that we have it, so we will define a projection operator phi n, that is 1 minus sum over k not equal to n. Okay, so this is the projection operator that we have defined. No, not sorry. Okay, not like this. So this will be, sorry, projection operator 1 minus. Okay, so in principle, this projection operator, so so every state, so that is connected by this thing here, this operator acting on the eigenstate on n, is actually it lies in this set. So in principle, this set spans to all the eigenstates that or to the everything that this operator can reach in the Hilbert space, which is good. And I'm going to just write this as sum over k not equal to n, and that will be k0. Great. So which is fine now. So now we can do somewhat of some different things here. We can see that. So if you have your phi n, and now that you have divided it by en0 minus of h0, it is in principle equivalent to sum over k not equal to n 1 upon en0 minus of ek0. I'm sorry. Okay, great. Now, in principle, one would like to have to do this step here. Take this down. Take this quantity over here and down here. But just a few steps before that. So lambda v minus of delta n get n is actually equal to phi n lambda v minus of delta n get n. The argument being is that if you add the n0 also, then it goes to 0, so that's not necessary. So it's in principle is equal, right? So now in principle I can write my get n. Well, there are like a few things more, but we'll explain that. And that will be n0 minus of h0, and there is this phi n and lambda of v minus of delta n. Now obviously, so there are like a few things here. As lambda goes to 0, n goes to n0, and delta n also goes to 0. So but this cannot correct, right, in that case, because everything will be a mess here. So this is not possible if lambda goes to 0 and delta n also goes to 0 and also approaches the unperturbed state. So it's not fine. So, but nonetheless, for non-zero lambda not equal to 0, we can add state something. We can do something like, okay, so get n equal to, sorry, Cn of lambda n0 plus 1 upon E0 minus of, okay, not like this. And there's this phi n lambda v minus of delta n. Great. Now, in principle, when lambda goes to 0, Cn of lambda, it should go to 1, right? So it takes care of things totally. And Cn of lambda is equal to, n0 this. So totally fine. Everything is okay. And but for reasons for now, like, we will save us from the curse of normalization, or like not the curse of normalization, but we will just for a moment we will just keep it aside. So, and we will put Cn of lambda to be 1. This is totally fine, because if Cn of n of lambda is not equal to 1, so we have to like introduce an additional common multiplicative factor, which can be settled later on, and it can happen, and it's not that hard to do that. So for now, I will just set this, and I'll have my get n as 1 times n0 plus 1 upon n0 minus of h0 phi n lambda v minus of delta n get n. Great. Okay, so for now everything seems fair and fine. Now, if you remember correctly, so if you remember this equation, wait, where is 1? Yes. So if you remember this, so we shown that we have shown this. So this implies that and just now we have set Cn of lambda to be 1, so this quantity is 1. So this implies that delta n equal to lambda n0 v times n. That's great. Okay. Now at this point, so now we will use the old trick. So we'll Taylor expand delta n in lambda, and we will also expand we will also expand get n in lambda, and then we will match powers, and we will get the perturbative series, similar to the earlier example. The idea there where we had picked up the powers of lambda in the two-level system, and we said that each of them is a correction, and how the different corrections emerge. Now we will do the similar kind of exercise here. Okay, so let's look at our final equation that we have here. We have n equal to get n0 plus phi n upon n0 minus of h0, and there is lambda v minus of delta n get n. which is good. And we have our delta n defined as lambda n0 v get n. Great. So let's do that. So let's write n in a power series, that is n0 plus lambda n1 plus lambda squared n2 plus higher order terms. And then we have delta n, and it's written as lambda delta n to the first order plus lambda square delta n to the second order plus lambda cube terms. Okay, so now let's go up here and okay, just for sake, well, let me show you that order of lambda 1 is delta n1, so which is nothing but n0 v n0, but just a scattering matrix probably in some sense. Lambda 2 is and similarly, if you have order of lambda n, so that will be delta n to capital N, that will be n0 v n n minus 1. So quite simple, isn't it? Okay, great. So this is all done here. Now let's do something. Okay, so we had n, written as again n0 plus phi n upon n minus of h0. And now let's put this quantity in the power series and n in the power series. So that will be lambda v minus of lambda delta n 1 minus of lambda squared delta n 2 minus so and so on. And similarly on the other side we will have n0 plus lambda n1 plus lambda squared n2 so and so on. Great. Now okay, so obviously, so for order of lambda, for first order terms, we have phi n v upon n0 minus of h0 get n0. So this is the first order correction, obviously. Yeah, I'm just saying that you just pick the lambda values and just look at the order. And now that because you have this thing, in principle, you can compute second order term lambda squared. So let's try to do that. I don't think the space is enough, but let's do this here. For the second order term, let's collect the second order things that we have, right? So, but before that, I think we need to compute delta n2. So yes, and that will be n0 v n1. And so n0 goes here, v goes here, and there is phi nv upon en0 minus of h0 n0. And now, okay, now we can use this to get the n2. Okay, let's see, let's get n2 first of all. So for n2, it would be, let's collect all the lambda square kind of terms. We will have lambda squared phi n n0 minus of h0 n2 okay. I'm sorry, no, there's something wrong. Okay, let's see. So lambda should go with lambda. Here lambda should go with lambda. And this lambda square should go with nothing. Okay, great. So we have phi n, this term in the front, and obviously there's a lot of calculation here. There should be v times n1. That's great. And now for the second order term, another second order term will be this this term out here going with this term, probably. Yes, and that would be minus phi n upon n0 minus of h0. There is delta n1, of n1, and then there is this term that is phi n delta n2 divided by okay, great, fair enough. So okay, now let's look at it in so okay, let's write these things down. This is fine, and then here we will have phi n, so delta n1 is wait, we need delta n1, right? Yes. Where was delta n1? Where we define delta n1? Okay, yeah. So this is delta n1. So then this has to be n0 v n0. Okay, I think I will just leave it as delta n1 probably. And the n1 is given as phi n v n0 divided by n0 minus of h. Now this term here, because delta n is nothing but a constant, and phi n will go and simply get will stick to delta n2, and this term is in principle 0. You should have to count that. So you have phi nv, phi n, again v n0 upon en0 minus of h0 is again en0 minus of h0, and okay, so like this, you can go ahead and compute different orders of corrections. And I know it might look really complicated, but in principle, when we will do examples, it's quite not that complicated. You can easily compute corrections of different orders. Okay, great. Okay, so now let's look at a problem, I would say. Not a problem, actually. Okay, yeah. So now let's look at how to explicitly write the energy shift. If you just want to look at it, so if you're delta n, so for the first order, it is lambda vnn plus lambda squared sum k not equal to n vnk squared upon squared and plus so and so on. And vnk is actually defined as n 0 vk 0. Okay, so this is the second order correction, and then you will have third order and all the higher order corrections. And similarly, you can do you can write your get n in terms of the unperturbed states as n0 plus lambda sum over k not equal to n k0 vkn 0 minus of ek0 plus lambda squared sum over k not equal to n sum over L not equal to n vkl vln, and obviously some terms here. I'm not going to write it because it's going to get too congested, and then you have vnn vkn and appropriate terms here. And so this is how the correction is. Okay, great. So obviously, so now there is a few points that we would like to mention here. So I know this calculation is like too much to grasp in one go. So I would ask you to go back and do this once by yourself. One can find the reference in Shakurai. The chapter is approximation methods, and there it has given really nicely. You can work out the details, and if you have any questions, just leave them in the comments. And so I'm going to end this here, and with a very simple note on a few points that one can have from this calculation is that the first one is the first order is that the first order energy, the first order in lambda, the first order correction, the first order correction is nothing but a expectation value of v, and that is your perturbation term. Second, so in the second order of lambda, if you realize, you have two connected states, and they are given as g squared upon so what this essentially tells you is that, say you have a higher state, higher energy state, and you have a lower energy state. So what will happen is, because of the gap in the energies, your higher energy state will go a little more higher, and your lower energy state will go a little more lower by the perturbation. So in principle, so this is called no level crossing theorem. So which essentially tells that even if you add perturbation to your Hamiltonian, at a higher order perturbation, they never cross each other. So the pair of energy levels, they don't cross the energy levels, they don't cross each other. And yes, So your energies are not like your ground states don't change. Your ground state and excited state won't change here. Okay. So I suppose with this is enough. And just to name the method, so this perturbation method is actually called Rayleigh Schrödinger. Sorry. Perturbation expansion. Great. And just on a very small note, I'm going to mention the wave function renormalization. Wave function renormalization. So it's pretty simple that because now that you have corrections to your wave function, in principle, you define a new normalized wave function as something Zn to the power 1 by 2 n, and in principle you have your wave function normalized to 1, and because you have set your wave function as n0 plus terms, so your in principle your Zn to power 1 by 2 is nothing but your overlap between n0 and your normalized wave function. So this is pretty easy to compute. And if you want to actually compute Zn, which is nothing but n, so you will have 1 plus lambda squared plus higher order terms. So for the second order, you would just realize that this is 1 plus some k not equal to n. So that is v kn whole squared divided by n0 minus of ek0 whole squared. And this implies that Zn, this is Zn inverse. Zn is roughly equal to 1 minus lambda squared sum over k not equal to n vkn squared upon 0 minus of enk whole square. And one small thing that one can observe, that your Zn is always the derivative of your energy level, your energy correction En with respect to En0. So this is a small observation, and this is correct for all n. Okay, so I think this is enough for this video. We have covered enough. And in the next video, we will look at some examples, how to use perturbation theory, which are more important. But with this, I hope you get the idea of how exactly we have formulated the idea of perturbation and how we're going to use it in time independent problems. And yes, okay, see you in the next video.